Good afternoon, friends. So, this is the last discussion hour for this course, and today we will revisit the concept of stability of dynamical systems. So, I picked this topic because stability is a very important thing in the dynamics and control of any systems. So, we will see how we can analyze the stability using what we call as the Lyapunov functions. So before we start, let's take a brief introduction of linear and non-linear dynamical systems. So dynamical systems are basically, you can think of as differential equations that are relating different quantities. So dynamical systems are mathematically equivalent to differential equations. So all the analysis that we can do is you can do it thinking of analyzing a set of differential equations also, but since those differential equations represent some actual system, so we say that okay, we are analyzing that system or that system stability, right? So generally we have seen that we represent systems as x dot is equal to some function f of time and again the state vector x, right? So and here the f can be a vector valued function, right? So f can be like f1 dx, f2 dx, right? I should also denote x as a vector since x is what we call as the state vector, right? And till fn. So this x is the state vector, which we will see going ahead how to formulate the state vector and all. So x, let's say, generally has a few components, x1, x2, xm, right? And t is time, right? So now these equations can be classified into different types based on different criteria. One is linear or non-linear, right? Another one could be autonomous or non-autonomous. So we will just restrict ourselves to these classifications. So linear system is where this differential equation is linear, and in the non-linear case, as the name says, the differential equation is non-linear. So an example of linear would be x1 dot is equal to 2x1 plus 5x2, right? And x2 dot is, let's say, x1 minus x2. So there are no terms where where x1 is being multiplied with x2 or x1 is being multiplied with itself, like x1 power something. So these equations are linear, and in non-linear you would see equations like x1 plus, let's say, x1 x2. So this x1 x2 term makes it non-linear. So this term, this is the non-linear term, right? And one more classification that I told about is autonomous. Right, autonomous dynamical systems are those whose equation is given as there is no explicit time dependence. So x dot is equal to fx, right? No explicit time dependence. So these are called autonomous systems. And non-autonomous systems. And non-autonomous systems are reverse of this, where there is an explicit time dependence. Non-autonomous systems. So there the equation has an explicit time dependence. Right. And yeah, so x in fact depends on time, but there is no explicit dependence on time in autonomous systems, right? So these are also called as time invariant systems, and generally you would encounter these systems only in all these analysis autonomous systems. So also called as time invariant systems. So what does time invariant means? It means that the function is not a direct dependence on time, right? So invariant means something that does not changes. Okay, now the next thing that we will see is the concept of equilibrium points. So till now we have seen that we can have a set of differential equations that represent a system. They could be linear, non-linear, autonomous, non-autonomous. These are only a few classifications. There could be others. In fact, there are others. And now we will see the concept of equilibrium. So what are equilibrium points? Like intuitively you can think of it as it's a point where basically equilibrium point is maybe gives us not a correct idea. Like it's a basically point represents to a state vector basically. So you can think of it as a position of the system, where if the system is in that position, then it stays there, right? It does not move away from that position. So in fact, let's say you have a pendulum hanging, so the bottom position is a equilibrium position, and the vertically upward position is also an equilibrium point, right? But the difference between those two equilibrium points is that one is a stable equilibrium point and one is unstable equilibrium point. So the concept of equilibrium point, with that itself comes the concept of stability of equilibrium points, which we will in fact see in a few minutes. So the first concept is equilibrium points is that the system, if you, let's say, leave the system at the equilibrium point and do not give any disturbance, right? So it will stay there, it will not change, the values, not the states will not change basically. So how to find equilibrium points? Like, so the system stays there. You can think of it as a sort of rest, right? So how to find equilibrium points? So at equilibrium point, this x dot is equal to fx is equal to 0, right? So basically what we do, we equate those equations to 0 and find at what value of x, what values of the state vector do we get this condition, right? And they could be like stable equilibrium points, unstable, or saddle points. So we'll not go much into these stability, different type of stability. We will see the stability of equilibrium points in context of Lyapunov functions, right? There can be different stability analysis, but today we'll cover the Lyapunov function based stability analysis. So as I mentioned, like the pendulum example, so let's say you have a pendulum, right? So the bottom position, right, this is the equilibrium point, as well as this is an equilibrium point, but this is unstable and this is stable. Why this is unstable? Because if you give any disturbance here, then it will fall down, right? It's quite natural. But in this position, if you deviate slightly from here, right, then it comes back, right? And here if you give slight disturbance, then it does not come back, it goes away, right? So this in fact gives us an idea of what a stable equilibrium point should behave like. Basically, if you disturb the system state, then it should come back to the equilibrium point or stay close to the equilibrium point. It should not move away from the equilibrium point arbitrarily, right? So that's a stable equilibrium point. Mathematically, if you write the equation of a pendulum, so example, pendulum. So the pendulum equation you can all write this is the dynamics of the pendulum. And how can you express it in this form, right? X dot is equal to fx. So first we choose a state vector, right, that x vector. So x vector, what you will take, so here our variable is theta, right? So one would be theta, another would be theta dot. This would be our state vector, right? So then x dot would be what would be x dot? X dot would be theta dot theta double dot, right? And what is this equal to? Theta dot is equal to theta dot, let's write here, and theta double dot, from this equation, the dynamics equation, we can write theta double dot is equal to minus g sine theta, right? So our x1 here is theta, x2 here is theta dot, right? This is x1, this is x2. Let me write it here explicitly. This is x1, this is x2. Okay, so now x1 dot would be theta dot, and theta dot is x2, right? This is the first equation. The second equation is x2 dot, that is theta double dot, which is equal to minus g's. I think there is a mistake somewhere. Yeah, I think this would be ml square. Yes, so this would be g by l. Yeah, so theta double dot is minus g by l sine theta, right? And theta is x1, so we can write minus g by l sine x1. So in terms of x1 and x2 only, what are the equations? x1 dot is equal to x2, and x2 dot is equal to minus g by l sine x1, right? So now this equation is in the form which we had wanted, x dot is equal to fx form, right? Now if you want to find the equilibrium points, so for equilibrium points, the derivative of the state vector should be 0, which implies that x1 dot is equal to 0 and x2 dot is equal to 0, right? So if you put in this equation in A, right? So x1 dot is equal to 0 implies that x2 is equal to 0, right? And x2 dot equal to 0 implies that minus g by l sine x1 is equal to 0, which implies that sine x1 is 0, and sine x1 is 0 when x1 is equal to n pi, right, of this form, where n is equal to 0, plus minus 1, plus minus 2, and so on, right? So what are the equilibrium points? The equilibrium points are n pi comma 0, right? So you can see, if for n is equal to 0, it will be theta is 0, so theta is 0 corresponds to this position, the bottom position, right? Theta is equal to 0, and this is theta is equal to pi, right? So these are, after that, the actual, in reality, the system, the positions would repeat themselves, right? Like theta is equal to 2 pi is here itself, same as 0, right? So For practical purposes, these two positions, vertically downwards, vertically upwards, are the two equilibrium points, which is also given, which we have also found out mathematically by using x dot is equal to 0 condition, right? Okay. So now that we are familiar with the concept of equilibrium points, we can now move on to stability. So stability of an equilibrium point, right? So what are the different notions of stability, right? How do we define that a equilibrium point is stable, and what kind of stability does it have? So let's say we have a system, an autonomous system, x dot is equal to fx, and let xc be the equilibrium point. Fxc is equal to 0. Xc is equilibrium point, right? Now the first is stable, just stable. So when does an equilibrium point, when do we say that an equilibrium point is stable, right? So let's say this is the equilibrium point xe, right? And let's define a small area around that point, like a ball kind of thing. So for stable equilibrium point, if let's say any solution starts from a point inside this ball, then as time progresses it stays inside this ball only, right? Then it's stable. If it happens, right, if it happens that it starts from here but it escapes, it goes away, it can, like, it has to stay bounded basically in some neighborhood of that equilibrium point, right? So this is stable, this is not stable, right? So mathematically what we say is, let's say let delta be a small positive number, and if, how do we define a small ball around a point? We use norm, right? Norm basically is the distance. So you can think that, let's say at time t is equal to 0, we start from a point whose distance from the equilibrium point is less than delta, right? Then at all times, like after starting from there, at all times this resulting trajectory also stays in a ball around the equilibrium point of some different radius, right? So this is, if this is satisfied, then we say that the equilibrium point is stable, right? So then there exists, and this is also greater than 0, this epsilon, right? So basically what is the idea? That if we start in a neighborhood of equilibrium point, then the solution also remains in the neighborhood of the equilibrium point. It does not move away from the equilibrium point as for all time after t0, right? For all t greater than t0, for all t greater than t0. If at any time in the future it goes away, then it's not stable. It has to stay there for all time, like when t tends to infinity. So this is stability. Next is, and the reverse of this above condition would be unstable, right? When the solution moves out of the, does not stay constrained inside the neighborhood of the equilibrium point, then it's unstable, right? So that is trivial. Now there is a concept of asymptotic stability. Asymptotic stability. So in this case, the first condition is satisfied, right? The equilibrium point is stable, and additionally what we have, and the solution basically tends to the equilibrium point itself, right, as t tends to infinity. So what is the difference between stability and asymptotic stability? So in stability, the solution remains bounded, but it does not necessarily come back to the equilibrium point itself, right? But in asymptotic stability, if you start in a neighborhood of the equilibrium point, then on a long enough time horizon, the solution converges to the equilibrium point, right? A practical example would be the pendulum case, right? If you displace the pendulum, then it will oscillate, and finally it will come back to the vertically downward position, the mean position, right? So that's an example of asymptotic stability. So the solution always converges to the equilibrium point, right? So that is the concept of asymptotic stability. So we would use these concepts. So these are the concepts of stability. Now we will see how to decide, what's the method to decide whether an equilibrium point is stable, unstable, asymptotic stable, exponentially stable, right? So now we can start so basically what we want to know about the system is clear. We want to know the behavior of the solution near the equilibrium point, right? And a tool for that is what we call as Lyapunov function. So Lyapunov was a Russian mathematician, a 19th century Russian mathematician. 19th century Russian mathematician. Okay, so in the Lyapunov function analysis, we basically define a function which satisfies certain criteria, and if there exists a function satisfying those criteria, then we can say that the equilibrium point is stable. So first of all, let there be a system x dot is equal to fx, and origin is the equilibrium point. Origin is the equilibrium point, right? X is equal to 0. Now we have to find a Vx, a scalar valued function. Remember, it should be a scalar valued function, not a vector valued function. That is, it takes x but it returns a scalar. So what are the criteria? First is Vx and all its partial derivatives are continuous. So partial derivatives are basically these terms, del Vy, del Xi. So Vx and all its partial derivatives are continuous. Next criteria is Vx is positive definite. Vx is what we call as positive definite. So what is positive definite means? It means that V0 is equal to 0 and Vx is greater than 0 for all x not equal to 0, right? In some neighborhood of the origin or the equilibrium point, in some neighborhood. And how do we define neighborhood? We define that the norm should be less than some quantity of origin. So since we are, you would see that since we are looking at a certain neighborhood of the origin, the conditions that we would derive right now would give local behavior of the equilibrium point, like local stability. For global stability, we would have some more criteria. So right now let's continue with this. So first is continuous function and its partial derivatives are also continuous. Second is Vx is positive definite, that is V at the origin is 0 and at all other points it is strictly positive. And the third criteria is V dot x is negative semi-definite. Right, what does this mean? It means that V dot 0 is equal to 0 and V dot x is less than equal to 0 for all x in this neighborhood, right? Not equal to 0 obviously. So this, due to this thing is negative semi-definite condition. So negative comes because it's less than 0, and semi means, whenever you say semi-definite means it is less than or equal to. If it is strictly less than, then we call it as negative definite, right? So if a function exists which satisfies these criteria, right? If a Vx satisfying these criteria exists, then we can say that the equilibrium point is stable. Right, is stable. Note that we are saying stable, right? When can we say that it is asymptotically stable? Asymptotically stable, and that too locally, not globally. Locally asymptotically stable when the third condition, there is a small change in the third condition for asymptotic stability. For asymptotic stability, it should be negative definite, not negative semi-definite, right? So when V dot x is strictly less than 0 for all x not equal to 0 in the neighborhood, right? So this strictly negative, this term, if this is satisfied, then it's asymptotically stable locally, right? there is also one more stability notion which is called as exponentially stable. Exponentially stable, and this is also now currently locally. So this is true when v dot x is less than equal to alpha times vx for all x not equal to 0. Right? If this is satisfied, then the function is exponentially stable. Right? Now for global asymptotic stability, there is one more condition. So global asymptotic stable. So for that, all the above conditions, right? All the above conditions plus there is one more condition, that Vx should tend to infinity only when norm of x tends to infinity. Right? That is radially unbounded function. Radially unbounded. So if this criteria is also satisfied, Vx tends to infinity as norm of x tends to infinity, and all these criteria, that v dot x is less than 0 and these two criteria, then we will say that it is globally asymptotic. The equilibrium point has global asymptotic stability. Right? Now let's see some examples of how to use these concepts on practical systems. Right? So our first example, so these examples I picked from the lectures itself, so you would find them familiar. Examples. So the first is damped pendulum. Right, so damped pendulum is basically somewhat what you call a more realistic pendulum, where there is like drag effects and all. So an idealistic pendulum, if you disturb it and leave it, then it will keep on swinging, right? But a damped pendulum would come to rest after some time. So the equation for a damped pendulum is given as ml square theta double dot plus mgl sine theta plus b theta dot equal to 0. Right, so this is the damping term. This is the damping term. Right. Now we would do the same kind of things, right? We would define the state vector x1, x2, and this would be theta dot. Right, so if you again follow those steps, so in terms of the state coordinates, we can write the equations as x1 dot is equal to x2 and x2 dot is equal to and x2 dot is equal to minus g by L sine x1 minus b by ml square x2. Theta dot is x2, right? So x2. So this is the equation. Now let's put m and l is equal to 1. Let m l equal to 1. Then what are the equations? The equations are x1 dot is equal to x2, x2 dot is equal to minus g sine x1 minus b x2, right? Now, so this is our system which we want to analyze, right? This is our system. What are the equilibrium points? So you would see that x1 x2 equilibrium points are same as before, I guess. That is some n pi or k pi and x2 is 0. These are the equilibrium points. So the most important step in basically Lyapunov function is how to create such a function which satisfies those criteria, right? So that is where all the, it's both science and art, you can say. So for this case, let's take this function alpha times 1 minus cos x1 plus beta times x2 square, right? And alpha beta are positive numbers. So v dot is, if you do differentiate this, v dot is alpha minus, this is sine x1 into x1 dot plus 2 beta x2 dot, right? And for x1 dot and x2 dot we will put the values from here, right? So x1 dot is x2, so it will be alpha sine x1 into x2 plus 2 beta x2 into minus g sine x1 minus b x2, right? So v dot is x2 sine x1 alpha minus 2 beta minus 2 beta b x2 square, right? This is pretty straightforward simplification. Now if x2 is 0, right, at equilibrium x2 is 0, so if x2 equal to 0 and also at equilibrium x2 dot is 0, right? So x2 dot is also 0. So this implies that x1 dot is 0 and x2 dot is equal to minus g sine x1, and this is also equal to 0. So again x1 is equal to k pi, right? So our point of interest would be 0 0, right? Let's say this is our x 0 0. This is our equilibrium point, which is we know that this is stable and asymptotically stable. We know that because if we, as I said, if we perturb the pendulum about the bottom mean position and leave it, then it comes back to it after some time. So this should be asymptotically stable. Let's say if it is. So first, we have to check first that v0 equals 0, right? And if you see if you put 0 here, this is in fact 0, so this is satisfied. Now what else is that Vx is greater than 0. If you see here, this term is always positive, and since cos x1, it is always less than equal to 1, so this is also positive, so this is also satisfied. Now what about v dot x? So v dot 0 should be 0, and if you see v dot is this one, so if you put x2 0 and x1 0, so this goes to 0, so this is also satisfied. And the final one is that what about v dot x? So if we choose alpha is equal to 2 beta, right? So this term goes to 0, then this term which is minus 2 beta b x2 square, so this term will always be less than 0 because x2 square is always positive and negative that will always be negative. So v dot x is equal to minus 2 beta b x2 square and since alpha and beta are arbitrary, we can always choose alpha is equal to 2 beta so that the first term goes away, right? And this is strictly less than 0 for x not equal to 0, right? So this is all satisfied, and what can we conclude now? That 0 0 is asymptotically stable. Stable equilibrium point. Right, let me switch the color. Now let's see another example. Now let's see the example of controlled pendulum. So by control pendulum, we mean that we are actually providing some torque input, right? And we are trying to maintain certain position of the pendulum. So it's not just under the action of gravity, but we are also giving some external torque, right? So the equation of motion would be modified like this. So the terms on the left hand side would remain the same, and also it is again the damped case only, so damped pendulum with a control input, right? Plus b theta dot is equal to tau is the control input. Okay, so our state space equation would be x1 dot is equal to x2 and x2 dot is equal to tau by ml square minus g by l sin x1 minus p by ml square x2. and same as before, x is x1, x2, which are equal to theta and theta dot. Alright, so here also we put let m equal to l equal to 1. So x1 dot is equal to x2 and x2 dot equal to tau minus g sine x1 minus bx2. So now this is our system, right? And what is the change? The change is that in the second equation there is this tau term also, right? Now one practical problem would be, let's say we have to find a control input, find tau such that we maintain a certain angle of the pendulum, theta desired is pi by 4. So this is x1 desired, right? So basically we want to give a control input and we want to maintain the pendulum at a certain angle. So basically we would like that configuration to be stable basically, right? So let's see how to formulate the equations for this problem. So our desired state vector is that we have to, theta is pi by 4 and theta dot would be 0 because we want to keep it there. So it is at rest at pi equal to pi by 4, right? So we define the error as x minus xd. Okay, so let's write it component wise. So x1 minus x1d and e2 is x2 minus x2d, and since x2d is 0, so this is straight away x2 itself, and e dot is equal to x dot, since xd dot is 0. So this implies that e1 dot is equal to e2 and e2 dot is equal to tau minus g sine x1. So x1 is e1 plus pi by 4 minus b x2 is e2, so b e2. Basically we use these two equations, right? So this is the equation of the error, right? Error equation. And so what do we want? So for this system, so there are two systems here, right? First was the original one where we wanted our desired position was pi by 4 and 0. Now we wrote the error equation, and in error equation our desired would be 0 0, right? We want the error in both terms to be 0, so this is our desired equilibrium position. Okay, so we have to show that E00 is asymptotically stable, then only we can control it there, keep the pendulum there. So what control input we should give so that this 0 0 is asymptotically stable equilibrium point for this system, right? So let's choose a Lyapunov function. Let's choose a Lyapunov function v, the function of E, and let it be alpha times E1 square plus E2 square. Okay, and v dot is 2 alpha E1 dot plus 2 E2 dot, right? Let's put the value of E1 dot and E2 dot. So it will be 2 alpha E1 E2 plus 2 E2 dot is tau minus G sine E1 plus pi by 4 minus B E2. Okay, so this is our V dot. Now we have to select this torque, right? This control input we have to select. So how to select that? So if you would see that if we choose this tau such that the resulting expression here it becomes always negative, right? That's the case when we would achieve asymptotically stable condition, right? So we would choose tau such that this expression is, we can guarantee that it is always negative, right? So one such torque input is minus alpha E1. Basically we are selecting torque such that all terms which can become positive get cancelled out and only that term remains which we can guarantee that it will always be negative, right? So if you put this value of tau here, right, if you put it here, you can see that what will this become? V dot. Let me write it. So V dot for this value of tau is 2 alpha E1 E2 minus 2 alpha E1 E2. This G sine E1 plus pi by 4 will get cancelled, right? So what will remain? Minus 2B E2 square. This also gets cancelled. So this is minus 2B E2 square, right? And this is always negative because E2 square is always positive for E2 not equal to 0. Okay, so yeah, I mean we found a control input for which E equal to 0 0 is asymptotically stable for the above control input. Basically we are able to find a control input such that we achieve that desired position of pi by 4, right? So what does this mean? The error 0 0 is asymptotically stable. This implies that this position pi by 4 can be achieved and maintained, right? So this is how basically we can use the Lyapunov stability criteria, right? And the limitation one of this approach is basically how to choose the functions itself, right? So there is no generic method to define Lyapunov functions for different problems, different systems. You would have to come up creatively such functions to either prove or disprove stability, right? And there are certain ways, but again there are no generic ways that applies to all sorts of problems. So limitation is there is no generic method for building Lyapunov functions. Okay, so yeah, any doubts in this topic? If you would like to ask, then go ahead, please. So this is what I had planned to discuss from my side, and this is the last discussion hour. So I hope that this whole weekly discussion hour thing was useful for you guys in solving assignments also, and the exam also, the final exam also, which I guess would not be very difficult. So if you go through the lectures carefully, you would be able, I hope you would be able to solve most of the questions. Any comments from your side? Then otherwise then we can wrap up.
No doubt, sir.
Okay.
Sir,
Yeah, go ahead.
when from which age are we eligible for the IIT exam which you have been posting?
Can you repeat? I was not able to get it. Your question. Can you repeat, please?
From which age are we eligible to write the exam?
Exam for IT entrance.
Yeah.
Yeah, you do it by after like you give your 12th class examination, right?
After we finish our 12th class examination.
Yes.
Okay.
So you are in which class right now?
7th.
7th. So you are doing this course?
Yes.
Okay. So are you interested in robotics?
Actually, I am 2 times national champion in robotics and I am the world's youngest RPA developer.
Oh, wow. That's
I
great.
acted in some movies, some serials like that. I have many hobbies.
Okay, so have you built some robots at home?
Yes.
Like wheeled robots kind of?
Wheeled robots.
Okay,
Yes.
okay. So what was the competition that you participated in?
FLL and WRO. Do you know those?
Not exactly. So can you give me an idea? Like what are those? What happens there?
So means we should build some kinds of robots and explain about it. What I did is, so I created a bus which drives on its own and takes people and drops them in their place where they are supposed to go, like that.
Okay, so was it like an autonomous vehicle kind of thing?
Yes.
Okay, no driver, it just picks up people and drops in at their destination.
Yeah. Mostly like that.
Okay. So in this course, like, were you able to follow all the things, like mathematical things and all? Because I guess some things you might not have studied right now in your class level.
Yes, some things. Actually, what happened is I was in the week 4 and 5, I had some doubts, but I wasn't able to ask, sir. But
Yeah, if you want to ask, you can ask right now.
No,
But
no, now I don't need to because I got clarified with those.
okay, yeah, you got it clarified. That's good.
I'm going to build a tracked plus air robot, two in one kinda.
Tracked plus aerial.
Yeah, yeah.
Okay, so have you thought any particular application for which you would build this?
Actually, what I actually thought of using Arduino and Microbit, but
Hmm.
what happened is I was not able to understand the circuits kind of thing to make the robot fly. That's the problem.
Hmm.
So I thought of making this underwater robot instead.
Okay.
Tracked which goes underwater with an arm.
So basically, I guess you would drive it on the ocean floor, right?
Yeah, like that.
Nice, sounds cool. Yeah, so I did you attend the previous sessions also, like the sessions that I was conducting?
Yes.
Okay. Hmm.
Actually, I had a small doubt, sir.
Hmm.
So, to spin the robot around, so are we supposed to, for one wheel, are we supposed, means all around, means without using the wheel, I mean, with the tracks, how are we supposed to turn, sir, without using wheels?
Without using wheel, you want to spin at one place only, right?
No, no, not at one place. Wherever we want to go, I want to turn using a tracked robot. Can we do like that?
Uh,
No,
so
right?
for like yeah, in wheels we use that differential thing, right? Differential
Yeah,
turning.
means not means for this. If we want to turn the right way, in the right wheel we add less force, and in
Hmm.
the left wheel more force. Like
Maybe
that.
you can give different velocity commands to the outer wheels and the inner wheels.
Okay.
Like different velocity commands. Basically, whenever you want to turn, the outer ones cover more distance than the inner ones, right? So
Yes.
I am just guessing like this could be a possible way to give different velocity commands to the outer and the inner set of wheels. You can explore this.
Oh, okay, means I wanted to like turn with the track, but I'm not understanding how that will occur.
Hmm.
I built a tracked robot as well, means when I was like 8, I think. Now I'm 12.
Okay. Yeah, so you are planning to write the JE examination after 12th.
Yes, I'm going to.
Yeah, nice. And where are you from?
I'm from Hyderabad.
Okay, okay, nice. So I was not aware that class 7 student is also enrolled in this course, so it was nice talking to you.
Thank you, sir.
Okay, so yeah. So when is your examination for this course?
Good, sir.
When is the examination for this course? The final exam?
I actually don't know, means I don't check that much.
Okay, okay. It's fine.
Should I check? Again,
No,
1
it's fine,
minute.
it's fine. I just wanted to know if you would know it right now only. But yeah, it's fine. No need to.
No, I do know. The final examination for now is at April. I think it finished actually. April. It's at April.
Okay, it's in April, right? So it should
Yes.
not be conducted yet.
April 28th.
Okay, okay. So yeah, okay. Bye. Nice. And you should build your robots, and yeah, you should come to IIT and build bigger robots, basically.
Yes, sir.
Yeah. Okay.
Thank you, sir.
Bye.
Bye, sir.